Hello everyone. Today's class will be my longest recordings, full of very important information on homogeneous and heterogeneous nucleation, how to control particle size, the nucleation and growth mechanisms. So by the end of this recording, you will have some idea about how to create these different morphologies, different particle sizes, everything that Bilge Hoca has been talking about on how to have a real kinetic and thermodynamic control over what we're making. And if we were live in class, this would be the figure that I would show you and ask you what is the significance of this figure. And you can start this class by thinking about what's really happening in here. This is called the Lamer model of nucleation. As you can see, this is time versus reactant. What is reactant? This is A plus B going to C, like we're always saying. These are my reactants. So I am giving food to my reaction until here. The concentration of the reactants are increasing up to a point. That's called the supersaturation point. And then we go into the depletion mode, okay? So the reactant concentration starts going down, and that's where my nucleation and growth mechanisms start to form these nanocrystals. Okay, so this is a very important figure to start our discussion today. And this figures and all these results are taken from this paper here, Shape Control of Colloidal Metal Nanocrystals, from the Journal of Small, published in 2008. I highly recommend all of you to have a look at that. What we're seeing here is that there is a critical reactant concentration that is required for particle nucleation, and this is where my nucleation is starting to happen, okay? And that's what I want to control to produce these different size and morphology nanoparticles, which at the end has a direct influence on your catalytic results. So what we're saying is controlling nanocrystal shape provides an elegant strategy for example, optical tuning, like you saw. Similarly, chemical reactivity is highly dependent on surface morphology, and optimizing nanocatalyst morphology has become a prolific area of investigation. These exciting possibilities have raised the key question: can we traditionally control nanocrystal shape and surface morphology? So I'm going to try to give you the basic information on how to do that in real life. And let's talk about the 0D nanomaterials, okay? So we're talking about like quantum dots, nanoparticles, spherical nanoparticles to make our life easier. And in my previous classes, I think I had mentioned that there are two very general, well-known mechanisms to do that. The first one is the thermodynamic approach, where you control the generation of supersaturation, the nucleation and growth, or kinetic approach, where you control the reactant concentration, diffusion, solubility, reaction rate, those kinds of things, which at the end you end up limiting the amount of precursor available for the growth, like molecular beam epitaxy, which Bilge Hoca mentioned you about, or confining the process in a limited space, like reverse micelle, for example, synthesis methods. Okay, so this is a very, again, general and basic information on how we control things. And why do we want to do that? Because we want to not only create nanoparticles, but we want them to be in identical size, identical shape and morphology, identical chemical composition, individually dispersed or monodispersed, no agglomeration nanoparticles. Okay, so this is important. And for that, we have to have some information on what do we mean by crystal growth. growth typically involves two discrete steps. The first one is nucleation, and which is forming a particle out of nothing. And I want you to visualize this by let's see, by saying that this is a phase transformation reaction. Okay, so forming a particle out of nothing means I'm forming, for example, a solid out of a liquid phase. So this is a phase transformation reaction. This is a reaction, but this is the phase is changing. Okay, so there are a lot of things happening with the phase change and everything else. And growth is everything that happens after that. Okay, how my nuclei grows, in what environment, in what temperature, and so on. So if we control this nucleation and growth processes, then we'll end up controlling our nanoparticles. These are relatively complex processes that involves absorption, diffusion, and other processes, but we can have an understanding with some fairly straightforward thermodynamics, which I will try to mention you today. Crystallization is another important phenomena. Okay, it is first and foremost a phase transition through which matter is transferred from a state of high free energy in a solvated state to one of the low free energy in crystal lattice. Like Bilge Hoca mentioned to you so many times, what the system is trying to do is it's trying to reduce its free energy. Okay, then things happen spontaneously. So a state from a high free energy to low free energy crystal lattice is the main understanding of crystallization. And of course, during the process, it has diffusions and barriers. Okay, it goes up and down, just like in life. Okay, you have ups and downs, but at the end, you try to reduce your energy from a higher to lower energy state. And what we're meaning by crystallization or nucleation and growth mechanism is you have a solution here, and these little particles come together and form a solid, for example, crystal. And there are a lot of similar phase transition processes that happen in nature already, which resembles what we're doing as nanotechnology engineers here, which, for example, is the process of rain. The air turning into from like little dust particles into the raindrops, for example. It's sort of like a phase change reaction as well. All aspects of a crystal, including its phase, habit, and growth rate, are determined by the shape of this landscape here. Okay, and we're trying to govern this landscape here by doing some kinetic and thermodynamic approaches in our lab to make things easier and more controlled for our nanoparticle growth. Equilibrium, crystal habit, and phase are controlled by the depths and shapes of the energy minima. By varying the heights of the barriers, the growth kinetics can be controlled and non-equilibrium final intermediate states can be selected. All of these are taken from these books and journals. Okay? So we know that it's a phase change reaction, let's say, and we're trying to figure out whether a new phase will develop or not. And what we mean by new phase here is nucleation and growth. That's when my first nanoparticle appears in my system. The deciding quantity for a process to take place or not is the change in Gibbs free energy. Okay, that's very, very important. The necessary criteria for any phase transition to occur is that it wants to lower its energy. Okay, so the free energy of the system in its final state is lower than its initial one, and any transformation that results in a decrease in its free energy is possible. Okay, so we're trying to push our system in such a state that it happens spontaneously. I mean, you can't control the growth of your crystal non-stop all the time, but you can supply the necessary environment for it to grow by itself. Okay, so that's what we're going to learn today. The transformation needs not to go directly to the stable equilibrium state, but can pass through a whole series of intermediate metastable states. That's fine, okay? That's what we're trying to overcome. Crystals grow as long as their free energy of the system decreases with crystal formation. Okay, so we know that decreasing dg is spontaneous. This is equilibrium, and increasing dg, it doesn't happen by itself. You have to provide some sort of energy to the system for this to occur. And that's what determines if a thermodynamic process is spontaneous or not. Okay. And this is again a very basic information on what we're doing here. Actually, the change in the total free energy for crystallization of a single component is expressed with a change in the chemical potential of its crystallizing species, delta mu. This measures the free energy response to molecules transferring from one phase to another. Okay, so we're trying to find a mathematical expression on whether I'm going to have a crystal or not. Okay, so this is the chemical potential is another very important expression to define what we're trying to do in here. And let's say this is my phase transfer reaction. Okay, I have these different components, which in turn forms one bulk solid, for example. Okay, and Gibbs, the chemical potential is described as this relation here. Okay, this is like the products minus the reactants, okay? And then if you try to express this in thermodynamics, you end up getting this expression here. And if I define, let's see, this is, you can also call it as a big S, because I'm going to use this notation in somewhere else in my upcoming slides. This is called the how much saturated is my solution. This is defined by this expression. Okay, this is like the concentration amounts that I put into my system, and this is my equilibrium constant. So crystal growth can be modulated through controlling supersaturation. This is called supersaturation, which is very important. And that's what my Lamer curve looked like at the beginning. And this is my supersaturation point. Okay, this was the amount of reactants that I had, and this was my time. Okay, this is where the nucleation started. As soon as it's supersaturated, my solution, the nucleation starts here. Okay, and this supersaturation is expressed as the concentration differences of equilibrium and what I had put into my system. So the external factors that can influence supersaturation, which is the values of these KSP and CE, depend on solution composition, temperature, to some extent, to the values of activity coefficients, but presumably temperature is not as important for biological systems. Consequently, in order to manipulate these parameters, organisms must rely primarily on variations in solution chemistry. Okay, this is where the solution chemistry has a role. Okay, how much reactant I'm putting into my system to reach the supersaturation value. But of course, this whole system is also expressed or affected by, for example, the pH, the ionic strength, the impurities, and so on. Okay? So that's one thing, supersaturation. So number one, supersaturation. Keep that in mind, supersaturation, which affects how you reach this point. Okay. And then this is the degree of supersaturation, the concentration of the growing units in the solution, the equilibrium concentration of the growing units in a saturated solution. All of this affects my supersaturation value in that sense. And if you wanted to go into like the details of how this affects my Gibbs free energy, you have to go into more details of the definition of this in thermodynamics, which at the end will affect these parameters, which you don't know right now, but by the end of this lecture, these are the only things that will be most important to you, and we're going to see how this whole thing is affecting my R and delta G values. But let's see, for example, let's go a little bit into the details of how this Gibbs free energy is affecting my delta mu, and that's, as you know, in thermodynamics, defined as U minus Ts plus PV, for those who are more familiar with these expressions. And if you were to get the derivative, this will be du minus Tds minus SDT plus PdV plus VdP, right? And then dg will be equal to, since these terms will cancel out, at constant, this will be equal to minus S dt plus V dp plus mu dn, because TdS is equal to minus P dV plus mu dn. Okay. Anyways, this is the thermodynamic, this one is the thermodynamic identity for the G. And for fixed temperature and pressure, which is the case that is more common in our laboratories, then these terms will go away because they're constant, okay? And my dg will be directly related to mu dn. This was the result that I was trying to come, okay, from here to here. So in our case, that's where my chemical potential and the number of moles comes into play that affects my dg, because once you integrate these terms, it's going to be g is equal to mu times n plus a constant, which is 0, because mu is independent of n. Mu is independent of n. We are assuming that, okay? With this detail, let's continue. So what I try to show you is the importance of the chemical potential, how it affects the Gibbs free energy, and how these things are correlating with the supersaturation level here. Okay, so crystal growth is a phase change affected by a thermodynamic driving force, delta mu, and controlled by a non-equilibrium transport kinetics. Okay, at equilibrium, these chemical potentials should be equal because this is a phase change, okay? This is a phase change, like molecular epitaxy, not growth, molecular epitaxy. And the higher this gradient is, this is a gradient which drives the rate of my phase change, okay? So this is important to know. And now let's continue with what we're trying to achieve in this class. What are we trying to do? We're trying to form this nice little nanoparticle. And I want to control its morphology. I want to control its size. But we're going to have to understand what's happening in this system here. Okay? I've got these little reactants in my solution phase, and for some reason they come together and they form this nuclei. What drives the formation of this nuclei? Nucleation is generating a new phase from an old phase whose free energy has become higher than that of the emerging new phase. And we learned a little bit how that's affected by supersaturation level. Nucleation occurs via the formation of small embryos or growing units of the new phase inside the large volume of the old phase. Another prominent feature of nucleation is that the fact that it's metastable. We had seen those energy barriers, sort of like this. This is easily understood by considering the free energy chains associated with the formation of the nucleus. Okay, so let's go a little bit deeper. But there is this formation of nanoparticle. But what if I didn't have a nanoparticle? If this was my nanoparticle, this whole thing was a nanoparticle. Okay, I've got this huge volume here, but you know the answer of what is important, what's an important parameter in a nanoparticle is its surface area, right? Surface is huge surface area once you form these nanoparticles. So when you are dealing with nanoparticles, you cannot resist the factors that are added into the equation that is associated with the surface. Okay, and where is the surface? That's this. The surface is in between, let's say, a liquid phase and a solid phase. So I have an interfacial free energy there, interfacial surface there, that has a huge impact on what I'm making during the growth of a nuclei or during the growth of a nanoparticle. So the statement that the free energy per molecule of the new phase, the free energy per molecule of the new phase is less than that of the solvated phase only applies to the bulk of the new phase. Okay, when we are talking about bulk, we're talking about, if this is my nanoparticle, this is my surface, and this whole thing is the bulk. Okay, but as you know, once you start dividing your system into a lot of little nanoparticles, you increase the amount of surface area and decrease the volume. Okay, so bulk is the blue color and surface is the red color. Okay, so the free energy per molecule only applies to the bulk of the new phase, and the surface is a different matter because the surface molecules are less well bound to their neighbors than are those in the bulk. Okay, this is very important. In the bulk, the atoms are linking to these other atoms with all coordinations. Okay, with all coordinations. But once it reaches the surface, there will be molecules that are less bound to my bulk. These are dangling bonds. Okay, so its energy is huge. Okay, and so their contribution to the free energy of the new phase is greater. It's always positive. The difference between the free energy per molecule of the bulk and that of the surface is referred as interfacial free energy. It's called as surface free energy, but strictly speaking, this term should be reserved for surfaces in contact with vacuum. So surface free energy, interfacial free energy, okay, that's like the boundary layer for you between your liquid and solid phases, for example. And the interfacial free energy is always a positive term and acts to destabilize the nucleus. Okay, this is very, very important concept. I wrote so many things here. Let me clear up the space around this very important equation here, which is this one. Okay, so I have to define something else for the surface. Okay, that's called the delta GS. Okay, my previous definition applied to the bulk of the system or to the volume of the system, but here I have a different thing going on, and that's why I have to define something else. I'm going to have to call it like something like delta GS, S referring to the surface, and this is my surface area for a simple sphere, 4 pi r square times epsilon, or whatever is called the gamma. Okay, that's why I wanted to change the supersaturation notation. This is my this is referred as the for the surface only. So there will be a different energy associated with the surface of the crystal, because surface atoms have a different potential energy than bulk atoms because they are not bound to all atoms around them. Okay, just Keep this in mind like this. This is referred as surface tension. Okay, surface tension. This energy is always positive. What does that mean? It means it takes energy to form a surface. Okay, so the bulk part, the volume part that works with 4 over 3 pi r squared, let's say if that's the volume of a sphere, is always negative because of the thermodynamics. But here I have to fight against the energy that is related with forming a surface of a nanoparticle, because it always takes energy to form a surface. You can visualize that as trying to blow a balloon, for example. Once the balloon starts to get bigger and bigger, you have to try pushing, blowing harder and harder to keep that surface in shape. Okay, that's sort of like you have to always apply energy to form this surface here that differentiates your solid than the liquid. So delta GS is always proportional to the surface area of the crystal, and that's my surface tension. Okay, this is what I tried to draw. The molecules at the surface possess additional energy by an amount that's equal to the missing contribution to its bonding. Okay, and you can read a little bit more detail on what that means, but I already talked enough of this phenomena. And now we're at a very important point of this lecture where we try to define the whole mechanism in one big mathematical term, okay? And that's what we had been talking about, the delta G. But now we know that it is formed of two complex mechanisms. The first one is the bulk, what's happening in the bulk form, and what's happening on the surface of my nanoparticle, or what surface of my nuclei. So a spherical model of having interface between two materials is my model, forming raindrops in the atmosphere, forming a nanoparticle in liquid or gas, etc. Everything can be expressed by this equation. If you want to more define this in a more detailed way, you know that I have the chemical potential of the bulk and the surface. Okay, this is the chemical potential of the bulk form, which is affected by all that supersaturation levels and so on, the temperature, the pH, the impurities, whatever. And then this is affected by the surface tension. But this is, oh God, I have to change color. This is a surface term that affects delta GS. So this is affected by R squared, okay? And this is a volume term. This is a volume term, delta G bulk, and that is correlated with R cube, okay? Why this R is important? This R is important because this is what I'm trying to form here, okay? And I'm trying to control the size of this R. What is R critical? What is the minimum size of a nanoparticle that I can form is governed by this mathematical equation, okay? So that's why this R star is very, very important. If I can define this, then I know what would be the minimum size that I can form to grow, let's say, gold nanoparticles or whatever you're trying to grow. So this is the volume term, and this is the surface area, R squared and R cubed. Let's think about the total free energy is proportional to the total amount of material. Anytime you have an interface between two materials, okay, solid liquid, solid gas, etc., there is an increase in energy associated with the atoms right at the boundary between these two materials as a result of the under-coordinated sites with respect to the bulk. And we had learned that in this slide here, okay? And so this is always positive. Do we like positive? No, because things like to happen spontaneously, okay? We have to find a way to lower its energy. This always wants energy. You always have to blow into this balloon to form that nanoparticle. It always costs you energy to form an interface between two material. On the other hand, it can be energetically favorable to precipitate a solid. So, okay, energetically favorable to precipitate a solid, that's the delta G bulk section. If you reach a certain supersaturation level, it's going to precipitate. And we know a lot of examples that happens due to that, right? And if you have never seen it, you can just search the internet and see, you know, the supersaturation level, watch videos about it, and see how things happen spontaneously as you reach the supersaturation level. Of course, there are a lot of tricks related with supersaturation level as well, but that's the basic understanding of what's happening in delta G bulk. So these two terms are in opposite signs. Oh, that's great, right? Do I have any other colors? Green. Let's pick this one. Okay, so this term is negative. This term is positive. I need to supply energy for this one, while this looks more likely to happen spontaneously. And this is a volume term, and this is a surface term. So this is a r cube term, and this is an r square term. Okay, you can think, oh well, this is r cube, this will affect more, right? And this will affect less because this goes faster, so it's always going to go, you know, to the negative side. But that's not the case. There is an r critical that we have to guess where it's happening at, where the negative term starts to govern this reaction. Okay, this is another summary of what we're talking here. This is a very nice summary because this is my nanoparticle with R critical, okay? And as things grow, as you see, the bulk volume is increasing, okay? So I have a volume term and delta GV or delta G bulk, and the surface area and my surface tension here. If the particle is small, all atoms are at the surface. Look, this is small enough that all my atoms are at the surface. There is no bulk atom here. If the particle grows a little bit, this one, we now have some at the surface and some at the bulk, but still most of them are at the surface here. As it continues to grow, now most of the particles are at the bulk in this case, okay? So with bulk material, we neglect this surface term since vast majority is in the bulk, but when we get to nanometer scale, okay, increasing fraction of atoms are at the surface and these guys are in the uncoordinated side, okay? This is very important. This is what is making a huge difference according as a factor of going to nanometer scale. So these atoms at the surface have higher energy by the virtue of the fact that they cannot adopt a normal molecular coordination, okay? Surface free energy, surface tension, and so on, energy per area of force or per length are my units here. And so now we're gonna try to summarize all of this, everything that we had talked about in a single graph to see what is happening here during the nucleation and growth phases, okay? And this is for homogeneous nucleation, of course. This is my radius as a factor of, as a function of free energy change delta G, okay? So this graph includes everything that I care about, delta G versus R. And as you can see, surface free energy delta GS is expressed with 4 pi r square because it's a matter of surface times surface tension. Is always positive, okay? This here, the red line here, this is always positive. And my bulk term, blue is what I want. Okay, my bulk term is a volume term and this is always negative as my R grows, okay? And where does the nucleus form? The nucleus forms at this R critical, at this point, at a very short, this the, when, and if you sum this up, the blue and the red, this gives me the total free energy. And when the nucleus is, or the radius is too small, when I'm trying to form this nanoparticle here, first, this is governed, the whole thing is positive first. So I have to supply something to get over this hump. This is there's a hump here. This is R critical and this is G critical, okay? This is the thing that I'm trying to get over with, okay? And if I reach this point, if I reach this R critical, then everything is going to happen spontaneously and it's going to grow by itself. This is my growth phase. Yeah. And this is the nucleation and this is the growth. So volume, bulk, free energy, stabilizes the nuclei and it releases the energy, this one, the delta G bulk. And this is called the critical nucleus. For R less than R star, nuclei shrink, and that means that it destabilizes, it just disappears, okay? It tries to form this, you know, this little nuclei, they come together to form this nanoparticle, but until it reaches a certain size of R star, it's just going to destabilize. It will dissolve into the solution. Once it reaches my R star, it will form my nanoparticle, and this is the smallest size that I can obtain for this particular system. Okay, so that's why this term is very, very important. Okay, and this is the significance of this graph. So, if we were to go back to our Lemaire graph, you can see that I have three regions here. The first one is the pre-nucleation period, where I need to give something to the system to make it happy, so that it's going to reach here, so that it's going to form my nuclei. And then the second phase is called the nucleation period, and then I have the growth. And depending on the type of my figure, type of this whole energy profile, you control these different morphologies, particle sizes, and so on. Keep in mind that, okay, I really want to reach this point here, but I also want to control here, right? I don't want to, if this is like, let's say 10 nanometer here, I don't want to have, maybe I want to, all I want is like 10, 11 nanometer. I don't want it to have like 100 nanometer for my particular application. So I should be able to, I don't want this to continue growing as long as it wants to towards here as well. So I want to stop it somewhere, okay? By either temperature, by some way. And we talked about this reverse micelle process or the temperature or something. Okay, you want to stop it from growing as well, because we want to make this nanoparticle here. So the things to keep in mind, I tried to give bullets here for those parts. There is a barrier that needs to be achieved, okay? This is my barrier, this part, this whole thing, this is my barrier. I need to get over that. Once you get over this barrier, then you get both nucleation of particles and you get growth, okay? These two phases here. So you're manually increasing the concentration in this particular case. And remember, this was called the supersaturation level. Once you hit supersaturation, nuclei begins to form and concentration in solution will start to decrease. That's the summary of this curve, which is very, very important to know. And controlling the size distribution is tricky. We don't want the large ones to grow. The smaller ones would like to go away at the expense of the large ones, okay? That's also very important for you. It should be. So, again, this graph, we know this one, are critical. G star, this is the activation barrier to nucleation. This is what I try to get over. I want to get over the G star to reach R star, okay? Particles that are smaller than the critical nucleus will evaporate. We already talked about that. Particles that are larger than the critical nucleus will grow. And this process is called, for example, Oswald ripening. Okay, this is very important. And this is how the particle size looks like as time goes on in the system here. At first, and if this is our critical, at first I have some, not our critical, this is not our critical, this is some sort of let's say the size of the nanoparticle that I want to achieve. Let's say this is like 10. Okay, I want to have a size distribution here that looks like this. Oh my God, that would be so good, but it's very hard to achieve because at the first hours of your process, you're going to have these nanoparticles as well as these ones, and then you will have more differentiation between these two size regimes, okay? But as the time goes on, what's happening as the time goes on, here I'm in here for this part, this will disappear, the little ones, and I'm going to have a big, huge, broad nanoparticle distribution size, okay? So I want to, and that's called Oswald ripening. I want to control what's happening here to get a good size distribution. And that's controlled by, the kinetic and thermodynamic, the temperature, the concentration, the pH level, and so on. It has a huge effect on all those factors. So what we learned is the newly formed nucleus is stable only when its radius exceeds the critical size. A nucleus smaller than R star will dissolve into the solution to reduce the overall free energy, whereas a nucleus larger than R star is stable and continues to grow bigger. And that's what is happening here. Okay, an important question for you would be to drive R star and delta G star to exactly see what is affecting these two things in my nanoparticle growth. Okay, and if you do that, which I'll try to do it now with you if I can, you're going to come up with these two equations. So can we do that now together? How do we do that? What is this before that? What is this point here? This is where the d delta g t over dr is equal to 0. Okay, that's how you do all the equations to reach the R star and delta G star. Now I'm going to try to do that if my mind allows me. So we're trying to do the delta GT over dr is equal to 0, and that means d over dr 4 pi r square plus my volume term, the GV, okay? And that is equal to 8, let's do this, 8 pi r plus, and let's put a star here to define that it's R critical, and 4 pi r delta GV. Okay, and 8 pi r is equal to minus 4 pi r delta GV, and then R star is equal to over delta GV. I think I did something wrong somewhere, but we can get over that. Okay, This is bulk, volume term, or bulk term. Okay, even if I did something wrong here, I'm sure you're going to be able to do this derivation. Oh, that's the word that I'm trying to come up with. Derive this, okay, guys? And you obtain this, and that, you know, can also be expressed from the chemical potential point of view. And again, in thermodynamics, well, if you put this R star into the delta G term, the R star that you derived, if you put it into your delta G term, then you're going to derive the delta G star. Okay, so please make those derivations to understand what's really going on. And if you insert a thermodynamic notation for delta G bulk, which is delta H times delta T over the melting point of your, let's say, nanoparticle, and this is the temperature of the system minus the melting point, for example, and this is the latent heat of fusion, let's say. This is always a negative term when a liquid becomes a solid, which makes R star a positive value. Okay, so this is always positive. And if you do that, if you plug this into here, because I'm trying to express things with an easier and simpler expressions, this is what I will get. Okay, that's negative, and I have now a temperature that I can define. This is defined, and this is the delta T. And as you can see now that since these two are weakly dependent on delta T, you can see that the R star is decreasing as delta T is increasing. So the higher the temperature difference, you can decrease your R critical. Okay, so what you have to do is you have to, for example, supercool it. If you supercool it, you will end up increasing your delta T, which will give you lower nanoparticle sizes. Okay, this is a simple mathematical way to show what really affects this R star in a real factory process. For example, supercritical cooling, for example, is done for that purpose. So one way to achieve this point, okay, so yes, so you can control supersaturation, you can control the delta T, so you can really cool down this temperature, okay, to have a better control of R critical. But there is another way to do that. And to understand, if we were live with you, and maybe we'll discuss this during our live class on Tuesdays, but what do I need to do to lower this? I need to manipulate this this energy diagram here, and let me clean this a little. Okay, what I want to do is I want to get a lower R star, and for that, if this is my curve right now, if I had a curve that looked like this or this, for example, then I would get lower, smaller R stars, right? This R stars, let's say 1, 2, 3, 1 less than 2, less than 3. So I have to be able to manipulate this graph. And another way to do that, okay, this does that, okay, supercooling it does it. You have to, you reach it maybe here, okay, here, but it's not really doing that. I want to lower the delta G. How do I lower the delta G? Okay, this lowers the R critical, but I really want to do is lower the energy. And one very good way to lower that energy is to create defects in our systems. And as Bilge Hoca mentioned in a lot of points of his lectures, these defects or these dislocations end up giving you low G stars, okay? Why? Because let's say these little cubes here represent, each of them represents an atom in solution, okay? Once you create a defect here, because of that coordination numbers that we had talked about, these have different coordination numbers, and these things will go and attach themselves onto these defects. This will be the first thing that they're going to do, because these defects lower the energy profile that I mentioned to you at the beginning of the class. Okay, if this is my energy profile, or if this is the energy profile, once you create defects, you start decreasing the energy, the hump, the barrier that the system needs to create this first nuclei here. Okay, these dislocations are very good methods to lower the barrier of the system. So a screw dislocation is a defect where the crystal structure has been sheared in one direction. When atoms bind to the edge of a screw dislocation, the screw edge simply moves forward, causing a growth spiral. And maybe some of you had seen the spiral growth. This figure here shows the spiral growth. This, I think, is taken by an AFM measurement, and you can see how this crystal surface grew in a dislocation, in a spiral form. And that's why this is, you create this on purpose if you can, and then it's going to just continue growing this way, okay? And that's going to decrease your energy barrier. Screw dislocations are used to grow nanowires as well. If you manage to create your dislocation here, those new atoms that comes from your solution will always go and make this grow, which will turn out to be a nanowire. If we start with a small nanocrystal with a screw dislocation, then the nanoparticle will preferentially grow along one direction and can turn into a nanowire. So in this way, not only I decreased my delta G, but also I can grow nanowires instead of a nanoparticle, okay? So this is a very well-known fact on nanocrystal growth as well, these dislocations or the defects that are created on the systems. And sometimes to do these kinds of things, people put like impurities into their systems, because these little atoms will go and attach themselves onto impurities, because that requires less energy for it to form, okay? So by doing that, you actually help your system to get over the hump. And nucleation offers a way to get over the hump, okay? You can ask yourself, why does the phase transition in reality starts at impurities or rough boundaries? Another important thing is rough boundaries. Rough boundaries, impurities, rough boundaries. Nucleation starts at these sections of your system, just like dust particles cause rain, for example, okay? Let me see, okay. So one way is by having some help from an impurity. And this is where nucleation comes into play. Nucleation offers a help to get over the hump, okay? And you know what I mean by getting over the hump now, okay? This is my hump. Why do I have that hump again? Is a question that can be asked to you at some point. why do I have it? Okay, so I'm asking it to you now. I'm going to ask it in my life class if I remember, but why do I have this hump? And how can I lower it? Having some impurities, nucleation offers a way to the system to get over the hump. And why does phase transition in reality start at impurities or rough boundaries? Why? Because that creates a heterogeneous surface, and this is the delta G required for a heterogeneous system, which lowers your boundary. The amount of energy required to get over the hump is lowered here when you have an impurity or a rough boundary. And that can be thought of, let me try to explain it here again, if I can. How do I put a new page? Okay, so I'll try to draw it to you now. For example, let's consider the boundary of one of those impurities. Okay, what does it look like? Let's say my boundary looks like something like this. Okay, this is my impurity, this is my rough surface. Okay, this is my impurity, and let's say I'm a solution here, or this is like gas. Okay, and let's say I'm forming, when the first thing that the place that this gas molecule will go first is here, and let's think that we're trying to we are filling this with liquid. Okay, liquid is forming here. As you can see, as the liquid is forming here, the volume is increasing. Okay, the volume is increasing, but the surface area that is open to the system for formation, the surface area is constant. Okay, and if you want to consider, if you really want to simplify things, let's say my surface looks like this. This is my rough boundary. Okay, and this is where my liquid is forming. Okay, as it forms here, you can see that the surface area is the same, the volume is increasing, surface area is constant. And what does that mean? It means that my R square term, okay, because this leads to this positive side, right? This is the R square term, and this is where the R cube is governing my delta G graph. So this the part that is responsible for the things to be, that is making things harder, is the surface area term. And if things happen at boundaries of solid impurities, the surface area is minimized, and so this thing is minimized. It goes to a lower term. Okay, and that's why these things prefer to happen at impurities and rough boundaries, because you end up minimizing the R square term. Okay, and that is the answer of these questions here. Okay, which I'm going to definitely ask you. Okay, if you haven't understood this, we can discuss more in class with you. And another way to control shapes is by ligands. And let's say this is the nanoparticle that you had created, and it has some certain amount of positive and negative sites, equal number of green and gold atoms of different types. Let's say one is somehow green and one is positive, one is negative, or one is green, one is gold, one is something else. And you can manipulate these atoms, and here the faces that are enriched in green. Look, you can manipulate, you can play with your system. This is more green. Okay, or you can manipulate it and grow red on the edges, for example. And you can find such ligands, such organic molecules, ligands, that specifically go and attach onto different crystal faces, okay, crystal faces. For example, there are ligands that only grow on 111 or 100, okay, because they want to minimize their energy. That's all a matter of that. So that's why those ligands go and attach themselves onto certain sites. And what happens is, once these ligands attach themselves onto these, let's say, gold atoms, the reactants, the food that you apply, won't be able to reach there, and so you're gonna get a preferential growth in your nanoparticle. So you'll have an inherent difference between phases. One phase can be terminated with gold atoms, for example. You will often have organic ligands that could bind to surfaces of nanoparticles and change the overall energetics. Ligands can preferentially bind to certain phases, whereas other phases will continue to grow. It will change the habit of growth. Okay, this is important. The habit of growth is changed. So this, for example, this nanoparticle here will grow on the green atom site. Okay, and that's how people, for example, grow gold nanoparticles in rod shapes. Okay, what people do is, this is a very well-known ligand. It's called cetyl-3-methylammonium bromide, that that binds more strongly to some crystal faces than to others. And in this case, for example, the ligand is bound to these edges here, and so they stopped growing, and this thing will only grow in this direction, and that's how you're going to get like nanogol. So preferential adsorption of these ligands onto particular crystallographic faces, like C-tab adsorption, ends up giving you nanorods. Okay, this is how you control the nanoparticle shape. An example to do that. Okay, so this is important. How you control this? Why is it negative? Why is it positive? The volume term, the surface term, the impurities, how I control the overall energy behavior is very important to understand. And that's the end of my class. Please ask me any questions you have after you listen to this class. I will try to discuss more on this topic in our live session.